Section: Introduction. In this section, we discuss the importance of selecting the right data for training a language model to develop various skills, such as coding, understanding scientific texts, and engaging in conversations. To do this, we combine data from different sources, like code files, research papers, and chat logs, in specific amounts, a process we refer to as data mixing. Finding the best combination of these data sources is crucial for the model's performance. However, testing different combinations through trial and error can be very resource-intensive, requiring numerous training sessions. Recent advancements have introduced two types of data mixing algorithms: offline and online methods. Offline methods involve running multiple training sessions with different combinations, creating a model to predict performance, and then using that model to find the best static mixture. In contrast, online methods adjust the mixture proportions during training based on the model's performance metrics, like loss and gradients. While both methods need at least one training run to learn the proportions, they are more efficient than brute force approaches. When we evaluated existing methods, we discovered that none consistently outperformed stratified sampling, a straightforward approach that mixes data uniformly without needing extra training runs. This unexpected finding indicates that current methods share some common limitations. To advance data mixing, we set three goals: to deepen our understanding of the assumptions behind existing methods, to evaluate how these assumptions hold up in practice, and to use our findings to create new, principled data mixing methods. We enhance our understanding of data mixing by showing that many existing methods can be framed within a unified optimization approach we call linear mixing optimization, LMO. This framework addresses an optimization problem that aims to minimize the average loss for each data group while adhering to specific mixing rules. We find that all current mixing rules share a similar structure, with parameters that define how losses relate to mixture weights. Existing offline methods typically assume a static mixing rule, while online methods use a dynamic one. Each method approaches the optimization problem differently, with offline methods solving it directly and online methods using a greedy approach. Our framework clarifies the assumptions of each method regarding their mixing rules and how they solve the optimization problem. We then test the validity of these assumptions, finding that both static and dynamic parameterizations accurately reflect the loss proportion relationship across datasets. However, we also discover that methods can misconfigure their parameters, leading to subpar performance. By comparing each method's parameters to optimal ones, we see significant discrepancies that correlate with how well they perform compared to stratified sampling. Finally, we validate the assumptions made in the optimization process, concluding that the greedy approach in online methods is a reasonable approximation. Our analysis reveals that while the parameterization and solving strategies of existing methods are generally sound, their parameters often are not. To validate these insights, we introduce Aioli, a new online data mixing method based on the LMO framework. Aioli uses a similar approach to existing online methods but directly estimates parameters from the current training run, allowing for dynamic adjustments without extra training sessions. We evaluate Aioli by training models on various data combinations and find that it consistently outperforms stratified sampling across all datasets. Additionally, in scenarios with limited computational resources, Aioli's ability to adjust learned proportions during training improves performance in most cases. Section Summary. In this section, we discuss the importance of selecting optimal data mixtures for training language models and introduce our new online data mixing method, Aioli, which dynamically adjusts mixture proportions based on training performance. We demonstrate that Aioli outperforms existing methods, including stratified sampling, by effectively estimating parameters from training data without requiring additional training runs. Section: Problem Setup. In this section, we formalize the data mixing problem and establish our notation. We have 29 different groups of text data, including sources like GitHub, Books Corpus, and Archive. For each group, we receive training, validation, and test sets, which we label as the 17th group. We define our data sets accordingly. During training, we present the model with a total of 46 examples from 47 over 48 training steps. To illustrate how data proportions can vary during training, we divide the process into 26 equal rounds. Each round uses a mixture proportion derived from a probability simplex. Static mixtures rely on a single round, while dynamic mixtures utilize multiple rounds. We denote our language model as 53, which we reference at the start of round 24, where it has been trained on data sampled with specific mixture proportions. We can calculate the model's loss for each group using the training, validation, and test data. The loss at the end of training can be expressed in our notation, and when the model is clear, we simplify our references. Our goal is to minimize the total test loss across groups by determining the mixture proportions that yield the best performance. This aims to create a model that performs well across various data groups, serving as a proxy for future performance. However, without additional structure, we can only solve this problem through brute force searching, which involves training many models. Existing methods address this by imposing implicit constraints, allowing us to set the proportions without searching. In the next section, we introduce our LMO framework, which unifies many existing methods under a single explicit constraint. We present the LMO framework by outlining the general optimization problem and explaining how it can represent several existing methods. The LMO framework consists of an optimization problem equivalent to the data mixing problem, with an added constraint that describes the relationship between training on one group and its impact on another group's loss. We identify three key components needed to set the proportions: the parameterization of the mixing law, the values of specific parameters, and the method for solving the problem. We express existing methods within the LMO framework by specifying these components. Before detailing existing methods, we discuss the preliminaries for expressing them in the LMO framework. We define what it means for a method to fit within this framework and present a result that allows us to convert between linear dynamic mixing laws and a method for setting proportions. A data mixing method can be expressed in the LMO framework if it can be constructed by specifying a mixing law parameterization, parameters, and a solution approach for the LMO optimization problem. This definition enables us to frame existing methods as solutions to the LMO optimization problem, even if they were not originally designed to minimize average validation loss. Section Summary. In this section, we formalize the data mixing problem involving multiple text data groups and establish a framework for training a language model, LM, using either static or dynamic mixture proportions across several training rounds. We introduce the linear mixing optimization, LMO, framework, which allows us to unify existing methods for setting mixture proportions and minimizing test loss, while also defining how these methods can be expressed within our framework. Section: Converting mixing laws into update rules. In this section, we convert mixing laws into update rules. When addressing the LMO optimization problem, a natural approach is to use exponentiated gradient descent, EGD, which updates the mixture proportions while keeping them within the bounds of a probability simplex. We present a lemma that outlines the EGD update rule for the LMO optimization problem, particularly when certain conditions are met. This lemma illustrates how we can dynamically adjust the mixture proportions to tackle the LMO optimization problem, and it is defined using the parameters of the mixing law. This allows us to relate how a method sets its proportions to the assumptions it makes in its mixing law. We then discuss four existing data mixing methods, showing how they fit into the LMO framework. A summary of our findings is available in a table, and we also comment on other related methods in the appendix, where all proofs for this section can be found. For offline methods, we introduce data mixing laws, DML, which utilize a static mixing law. This method selects proportions that minimize predicted validation loss, derived from specific conditions. It requires multiple training runs to avoid underdetermination. For online methods, we provide both a general description and an algorithmic outline for three methods. We demonstrate how these methods can be expressed within the LMO framework using a linear dynamic mixing law and the EGD update rule. The first online method, Skillet, is inspired by curriculum learning and adjusts mixture proportions dynamically. It uses a skills graph to represent interactions between data groups learned from additional training runs. This graph informs the update of proportions throughout training. The second method, do-re-mi, applies concepts from distribution ally robust optimization. It aims to minimize the worst-case excess loss using dynamic proportions, requiring 2 additional runs to establish a static reference model. The third method, Doge, addresses a bi-level optimization problem, updating proportions to minimize average training loss at each step. It uses a Taylor approximation for updates and also requires 1 additional run for a static reference. All 3 online methods follow a similar update rule. Our summary in the table highlights how these methods fit into the LMO framework, revealing the assumptions each method makes based on the specified components. We note that all mixing laws are either linear or log linear, differ in parameter values, and that offline methods solve for proportions directly while online methods rely on EGD for greedy approximations. In the next section, we will investigate the practical validity of these assumptions. Section Summary. In this section, we present the exponentiated gradient descent (EGD) update rule for solving the LMO optimization problem, demonstrating how it can be dynamically adjusted based on mixing law parameters. We also discuss existing data mixing methods, categorizing them within the LMO framework and highlighting their assumptions and differences, particularly between offline and online approaches. Section: Analyzing fidelity of existing methods with the LMO framework. In this section, we analyze the fidelity of the assumptions made by existing methods using the LMO framework, focusing on 3 key components: the mixing law parameterization, the values of the mixing law parameters, and the approach to solving the optimization problem. After detailing our experiments, we will discuss these components in order. For our data settings, we utilize a sampled version of Slim Pajama, which is a pre-processed dataset derived from Red Pajama, used for training open-source language models. Slim Pajama includes 101 data groups such as archive, books, Common Crawl, C4, GitHub, Stack Exchange, and Wikipedia. To gain a detailed understanding of data mixing, we create 6 settings by combining these groups. We examine 3 settings with 2 groups each: Archive, Stack Exchange, GitHub, C4, and Book, Stack Exchange. We also explore 2 settings with 3 groups: Archive, Book, Stack Exchange, and Common Crawl, GitHub, Wikipedia. Lastly, we analyze mixing across the entire Slim Pajama dataset. Regarding our models, we train GPT-style decoder-only language models with 160 million parameters, using a batch size of 102 and a context length of 103. We train for 105,000 steps for the 2 group settings and for 106,000 steps for the full dataset. To evaluate the true relationship between loss and mixture proportions, we conduct training sweeps over various mixture proportions. For the 2 group settings, we set the proportions to be uniform. For the 3 group settings and the full dataset, we draw proportions from the Dirichlet distribution. We investigate whether the mixing law parameterizations used by existing methods, log linear static and linear dynamic, accurately reflect the true loss proportion relationship. By fitting these parameterizations to our data, we find that both are well specified. We present full results in the appendix and discuss their applicability across different training scales and subsets. In our setup for the log linear static mixing law, we check if there exists a parameter such that the loss can be expressed in a specific form for all data points. We fit these parameters using complete training runs. For the linear dynamic mixing law, we explore if a certain parameter can express the loss in a different form, absorbing another parameter into it. We select a specific time step for training on a static proportion and then adjust values in subsequent rounds. Our results show that, on average, the mean squared error of the fitted log linear static mixing law is low, and the coefficient of determination is very high. Similarly, The average mean squared error for the linear dynamic mixing law is also low, indicating that both parametrizations effectively capture the true loss proportion relationship. We also analyze how different methods set their mixing law parameters and how close these are to the optimal parameters derived from fitting the true loss proportion relationship. We find that the differences in parameters among existing methods significantly influence their performance. We do not include DML in this analysis since its parameters are derived from full training runs. For each online method, Skillet, Do-Re-Mi, and Doge, we select a specific step and obtain the method-specific parameters. We then adjust the mixture proportions in the next round to fit an approximately optimal parameter that reflects the true loss mixture relationship. We explore the connection between these parameters and the performance of the methods. To express the similarity between the parameters in a way that correlates with performance, we observe that updates are influenced by the sum of certain values. The magnitude of these values is not critical since we can always adjust the step size. We propose a similarity score that averages cosine similarity and Spearman rank correlation, which is bounded between specific values, indicating the degree of similarity. Section Summary. In this section, we analyze the fidelity of existing methods using the LMO framework by examining the mixing law parameterization, parameter values, and optimization problem solutions across various data settings from the Slim Pajama dataset. Our findings indicate that both log linear static and linear dynamic mixing laws effectively capture the true loss proportion relationship, with high fidelity reflected in their low mean squared error and high coefficient of determination. Section Results. In this section, we present our results by plotting the similarity of each method against its improvement over the baseline of stratified sampling, which is set for all datasets. We observe that no current online method performs well across all datasets, and our metric shows a moderate positive correlation with loss improvement. This indicates that the accuracy of our estimates significantly affects the performance of online methods, and the parameters of existing methods are not consistently reliable across different datasets. We provide additional details in the appendix about how our estimates vary and the importance of certain entries. Next, we analyze the assumptions behind how existing methods tackle the LMO optimization problem. We find that the greedy approximation used by EGD does not greatly hinder performance compared to fully optimizing dynamic proportions, which has a vast solution space. Specifically, we investigate whether selecting certain elements at each step yields optimal dynamic proportions and find that this is true in most data settings. This suggests that the greedy approach can simplify optimization without a major loss in performance. We also discuss other potential solving strategies in the appendix. To validate our findings, we introduce Aioli, an online method based on the LMO framework. We identify two key components for Aioli: the linear dynamic mixing law parameterization and EGD, as their assumptions generally hold true in practice. Our main goal in developing Aioli is to create an accurate estimate of the true mixing law, which existing methods struggle to achieve. For estimating the mixing law, we note that for each group, we can learn the necessary variables by solving a system of equations. Instead of conducting extensive training sweeps, Aioli leverages this idea efficiently. In our LEARNPARAMS algorithm, we define a uniform distribution for all groups and allocate time for estimating our parameters. We then train in a random order and record the changes in loss for each group, allowing us to simulate a training sweep without excessive computation. Finally, we solve the equations to obtain our estimates. During each training round, we estimate our parameters and normalize them to ensure stability. We update the proportions based on our estimates and continue training for the rest of the round. Aioli is designed to enhance other data mixing methods, and we explore this further in the next section. Mixture proportions can be updated at the start or midway through training, with specific steps defined for each scenario. Section Summary. In this section, we analyze the performance of various online methods against a stratified sampling baseline and find that no method consistently excels across all datasets, indicating that existing parameter structures may hinder accuracy. We introduce Aioli, a new method that optimizes data mixing by accurately estimating parameters through a novel training approach, allowing for efficient updates without extensive computational overhead. Section: Experimental Results. In this section, we evaluate all methods within the LMO framework, including Aioli, in two scenarios. First, we look at an unrestricted training budget to see how Aioli stacks up against other methods in their original forms, as each method uses a different number of extra training runs to learn proportions. Second, we examine a restricted training budget to determine if Aioli can improve existing methods under practical budget constraints, where methods have less than a full training run to learn mixing proportions. Details on hyperparameters and experiments can be found in the appendix, along with ablations and downstream evaluations. For our data settings and models, we use the same configurations as previously mentioned, training for 166,000 steps for the 104 group settings and 167,000 steps for the full slim pajama. We consider 3 online methods: Skillet, Doge, Do-Re-Mi, and 1 offline method, DML. Additionally, we include grid search, which selects the 10 runs with the lowest average validation loss, and stratified sampling, which sets a specific value for all groups. We report the average test perplexity per group of the trained model, which serves as a proxy for downstream performance and reflects the objective in the data mixing problem. In our setup, we allow methods up to 169 additional training steps to learn the mixture proportions. Methods like grid search and DML can utilize the entire budget, while Skillet, Do-Re-Mi, and Doge use 170, 171, and 48 extra training steps, respectively. Stratified sampling and Aioli do not use any extra training steps. We evaluate Aioli with 172. Our results show that Aioli consistently outperforms stratified sampling across all 6 data settings by an average of 0.280 perplexity points. Other methods perform worse than stratified sampling in at least one data group, with differences of up to 6.9 points. The performance of Aioli and other online methods is also illustrated in a figure, where we observe that Aioli's similarity with other parameters correlates with its performance. Although Aioli's parameter similarity isn't always the highest, its lowest score is still significantly better than those of other methods, indicating that Aioli's parameter estimation is more reliable. We suspect that the poor performance of offline methods in larger settings is due to the limited training budget, and that increasing this budget could improve their results. We introduce the restricted setting because practitioners may not have the resources or inclination to complete multiple full training runs to learn proportions, especially as recent large language models require longer training on more data. Consequently, practitioners might only apply data mixing methods on shorter runs, leading to potentially suboptimal learned proportions. We investigate whether Aioli can enhance performance by dynamically adjusting previously learned proportions throughout the full training run. In our setup, we allow existing methods only 173 additional training steps to learn the mixture proportions, requiring them to learn over shorter runs of 175 steps each. For example, grid search will conduct 109 runs of this length. We evaluate each method by using the learned proportions from shorter runs to train the model on the full run of 48 steps, employing Aioli to dynamically adjust these proportions throughout the full run. We refer to this as Aioli plus the method used. Our results indicate that incorporating Aioli into any existing method that learns proportions over shorter runs improves average test perplexity in 28 out of 30 settings, with an average improvement of 1.202 points and a maximum of 12.012 points. Aioli also enables methods that initially underperform compared to stratified sampling, like Doge, to surpass it across all settings. In some cases, such as books, Stack Exchange, Aioli enhances methods that already exceed stratified sampling. This demonstrates that Aioli can improve a wide range of mixture proportions, regardless of their initial performance. In the 2 instances where Aioli underperformed compared to the base method still outperformed stratified sampling, with Aioli maintaining this trend and only slightly worsening perplexity by a maximum of 0.025 points. Section Summary. In this section, we evaluate Aioli against various methods in both unrestricted and restricted training budget settings, finding that Aioli consistently outperforms stratified sampling and enhances the performance of existing methods in budget-constrained scenarios. Our results indicate that Aioli improves average test perplexity across most settings, demonstrating its effectiveness in dynamically adjusting learned proportions throughout training. Section: Data Mixing. In this section, we explore data mixing methods and frame them as a multi-armed bandit problem, where the loss serves as the reward function. Concurrently, other research has also approached online data mixtures adaptively, using a credit assignment score to predict how data from each domain impacts loss. We represent this with a diagonal matrix, where the diagonal values come from the credit assignment function and the losses for each group. Recent studies have looked into mixing data for smaller models and applying those learned proportions to larger models. We can also simulate a model trained on a specific data mixture by averaging models trained on different data group partitions. We introduce curriculum learning, which involves training models from the easiest to the hardest samples. While early efforts focused on manually created curricula, later research has shifted towards model-driven approaches. Curricula can promote skills-based generalization or prioritize high-quality data to enhance performance on downstream tasks. We can view online mixing methods as a form of curriculum learning over data groups. For data selection, we can curate datasets by selecting data at the individual sample level. This includes data filtering, where we remove low-quality samples using simple rules or deduplication. Data matching, where we choose samples similar to a reference dataset based on embeddings or model scores. And data condensation, which aims to find a subset of samples that represent the entire dataset's characteristics. We also discuss hyperparameter optimization and truncation bias. Many data mixing methods require additional training runs to determine static mixture proportions before the final training. This allows us to treat data mixing as a hyperparameter optimization problem, helping to address inefficiencies in higher dimensions. However, both grid search and offline methods may perform poorly when hyperparameters are fitted on shorter runs. We note that popular hyperparameter optimization techniques manage truncation carefully, allowing some runs to continue longer than others, suggesting that general methods may eventually be effective for tuning data mixes. In our discussion, we propose the LMO optimization framework, which can represent various existing data mixing methods through their implicit mixing laws. We demonstrate that linear dynamic mixing laws effectively capture the true loss proportion relationship across datasets, although some online methods still struggle due to inaccurate parameters. This leads to the development of Aioli, which improves performance by accurately estimating parameters of the linear dynamic mixing law during training. We acknowledge that Aioli incurs additional inference costs during training due to repeated evaluations. We can reduce this overhead by using training loss as a proxy for validation loss, computing over a subset, or extending the duration of each run. The LMO framework opens avenues for future research, aiming to identify improvements in data mixing, such as parameterization, estimation, and solving for hyperparameters. We also seek to understand how to define data groups and how their partitions affect mixing performance. For instance, reorganizing subsets of datasets like C4 from common crawl into more distinct groups could enhance mixing outcomes. Additionally, we are curious about the conditions under which linear mixing laws apply and how to leverage potential non-linearities in data mixing. For reproducibility, we refer to the appendix for full proofs on expressing various methods using the LMO framework, details on our analyses, and instructions for reproducing our experimental results. Code for reproducing our findings is also available. Section Summary. In this section, we explore data mixing as a multi-armed bandit problem and discuss various methods for optimizing data selection and hyperparameter tuning, highlighting the LMO framework's ability to unify existing approaches. We also identify limitations in current online methods and propose future research directions to enhance data mixing performance and understand the implications of data group partitioning. Section: Ethics Statement. In this section, we discuss our focus on enhancing the efficiency and performance of training language models. Although our research does not directly tackle ethical issues, it can aid in the development of more responsible AI by optimizing training processes, which helps lower both computational costs and energy use.